Thank you. I got three topics I want to talk about today. First is our annual review of our annual surveys, where we are in terms of trends in that. Secondly, I'm going to talk about, when we talk about status and trends, what do we really mean by status and trends? How can we quantify that any better than we do now? And then I'm going to finish up with an update on Cisco recruitment and how that may be related to climate. These are our good and plenty color-themed sampling locations because we consider them to be good sites, and there's plenty of them. So the black ones are a nearshore survey, which has been sampled since 1978 consistently. The pink dots are our offshore survey, and that's been sampled since 2011. And both of these surveys do bottom trawls, and that's all the data I'm going to talk about today is the bottom trawl surveys. And in 2018, everything went really well. There were no mechanical issues, there was no big weather issues, and overall, the nearshore survey and the offshore survey got lake-wide averages of similar biomass around 4 kilograms per hectare. And if you remember from previous talks, usually the offshore survey is much higher than the nearshore survey. This is our standard trend from 1978 for the nearshore survey. Those are means and 95% confidence intervals. We've seen an uptick, slight uptick in biomass since 2014, so over the last 4 years, 2015, over the last 4 years. And when you look at that time series, and Owen did a nice job of presenting data on this as well, is that total biomass figure is dominated by Cisco and bloater populations, to a lesser extent rainbow smelt populations, and also the lake whitefish. Our surveys do not do a great job of collecting lake whitefish all the time. It's mostly Cisco and bloater. And when we have recruitment events, and those are now shown in those pinkish brown bars, we see an uptick in biomass a year to 3 years after that. And again, that's mostly due to Cisco and bloater, and those bars show Cisco recruitment right there. So over the past year, our office has gotten at least 4 requests asking what's the status and trend on prayfish populations in Lake Superior. And the response always is the status and trends in what kind of metric do you want us to provide for that, and what's the time comparison that you want us to use when we talk about status and trends. So sometimes that's our eyes tend to fixate, and people always think about there's been these huge declines in prayfish biomass because they're thinking about what it was in the late 80s and early 1990s to what it has been recently. So that's the comparison that they're thinking of. But you can make other comparisons across other time periods. So if you go all the way back to the time series record, populations now are similar to what they were in the late 1970s. Also, we can use different metrics. Some of these reports want to talk about prayfish biomass. Some will want to use abundance. Some will want to use the number of native species, or the biomass of invasive versus native fish species. So we need to be cognizant of what it is that we're trying to measure or define when we present these. And this has ramifications when we talk about the fish community objectives, and because there's a bit of a undertow or that we want to start to quantify these. And if we're going to quantify those, that's great, but we want to make sure that we have well defined what those metrics are and how we are going to quantify them and over what time periods we're going to quantify them. So if we look at that same total biomass for nearshore data that I showed you before, and we'll just use an example here. We group it into 5-year periods, and it's basically those high years in the 80s and early 1990s. There's the low years, and then there's that transition period where we've been on that downhill roller coaster section of the track between those high years and the low years. If we break this out for individual species, we see a similar pattern that we see for, especially with the Ciscos of Cisco and bloater, where were much less during that middle time period than they are now. And what this does is it compares an average of 2014 to 2018 to these different time periods. And so over the last 5 years, there's been no decline or increase. Populations have basically been static for all these species. We see that middle period where they were much higher than they are now. And if you go all the way back to that earliest time period in the 1970s, they're similar to what they are right now. So this is just another way of looking at how we can define status and trends. Again, we have to pick the time period and we have to pick the metric. In contrast to our nearshore populations, which we saw a slight uptick over the last 4 years, offshore populations have declined in the last few years. And if we compare two time periods, 2017, 2018, compared to the average of 2011 through 2016, those are significantly less for kai, and they're similar for deepwater sculpin and Siskoet lake trout. An interesting observation that we've made with this offshore data, and the offshore data is 99% of the fish we collect are deepwater sculpin, kai, and Siskoet lake trout. And so these plots show the percent change between those two time periods that I mentioned and are shown right there. So the percent change in those populations, then all those 35 sampling stations are shown across the x-axis from shallowest to deep. And so those sites start at 85 meters and they go to 310 meters. And the big change here is that we've seen an increase in deepwater sculpin in nearshore sites, which are still offshore. So in those shallower 85 to about 150, 180 meter range. And a decrease at those deeper sites, say over 200 meters. Kai are down everywhere at these sites, and Siskoet are up a little bit in some sites and down a little bit in some sites. But again, that big change we've seen is less deepwater sculpin in those deepest sites and more in those shallower sites. And this is our recruitment index, the Cisco age 1 populations. And this has been done since 1978. Data is just shown from 1981, and there's a reason behind that I'll get to. And we collected one. So the index isn't one. We collected one age 1 Cisco in 2018. And that's the most dismal collection on record for Cisco throughout from 1978 to present. And so I think this has left these fish thinking, where are all the fish in the sea that my mother probably promised me? And so now I'm going to switch this talk to, can we explain what this variability in recruitment is, and is there an underlying cause? It's because it's not a pure random distribution of when these high events occur and when they don't. So to do this, we grouped each one of those recruitment events into three classes. The data is not at all normally distributed. It's highly skewed. A couple high values and one super high value and a bunch of low values. And so we class these based on which were breaks in this population, where the population is 37 years basically of recruitment index values. And this is what we saw. So for high years, there were high recruitment events were from 68 fish to 750 fish, and there were 7 years. Measurable, or I'll use the term moderate sometimes, there were 12 years, and none to low, where we got less than 2 fish per hectare, there were 18 of those events. And how we're going to analyze those, we developed a regression tree model, and in a regression tree model, you put in different environmental variables or biological variables, and here I've given an example of spawning population size, and then how much of that variation in those recruitment index does that explain. And this model does a nice job for low and high, and then you could break down those medium and high values with maybe an environmental variable like spring water temperatures, and this is all just hypothetical. And this analysis was done with the R-part package in R, and the only thing that we changed from default values was we set a minimum number of observations in that final node at 6. You can run it all the way down to 1, but if you are trying to predict something on one event, it's not very useful. And so 6 was just what we thought might be useful. Because again, it seems like we have a long history of 40 years of recruitment index, but trying to predict 40 things is not easy. There's a number of factors that go into determining recruitment or underlie recruitment. That includes what occurs during spawning, what occurs during egg development during the winter, and then so spring conditions after those fish hatch. And ideally, we would populate the model with everything that is shown here, or even additional factors. But unfortunately, there's only data for a few, and those are now check marked. So population size, we use some model output from Ben Rook's model, which he's going to talk about later today, to estimate population size. I went into the model of adults. For egg development, we used ice cover and water temperatures. For the hatch, we used water temperatures. We used rainbow smelt populations from our nearshore survey as an indicator of predation, potential predation on those newly hatched larvae. We used growth at size 1 to look at growth over their initial age 0 year to see if a larger fish might be healthier, and if you had more healthy fish, you'd have greater survival. So again, we started out with, we had 18 none and low recruitment years, 12 low to moderate, and 7 high recruitment years. So the first split in our tree was a really nice split. And so when we had January ice cover over greater than 15%, that been 6 of those 7 high recruitment years and 11 of the 12 moderate years. So there's only a single high recruitment year that didn't occur when we had January ice cover over 15%. And that one year was 1998. And that year was that huge El Nino year that occurred. And it's been that, there's been a lot of work that describes what they call the regime change in terms of Lake Superior environment that occurred pre-post 1998. This is what 15% January ice cover typically looks like on Lake Superior. So this is just a mishmash of a number of years showing ice concentration. And this ice concentration of 15% matches really well with the bathymetry out to 100 meters. So this is the 100-meter bathymetry line. So if you think about like where would ice cover, we can visualize where the 100-meter bathymetry line is. I've overlain this with index of Cisco spawning sites. Second time it's been mentioned, the Goodyear spawning atlas data. And all those sites fall within that ice cover and that 100-meter bathymetry line. So is this a potential mechanism? Because that's one of the things, a lot of people have done this analysis, probably been done a dozen times over the last 40 years. And the results have been mixed and matched, and sometimes good, sometimes not so good. But we also tend to lack a mechanism in those previous analyses. So we're trying to think about what could that mechanism be, whether is it just a spurious occurrence, that 15% January ice. That may actually mean something here, because it provides early egg coverage. Again, these fish are spawning in December, and then we get immediate ice cover over those eggs. One potential mechanism is the effect of ice on light, because ice certainly affects water temperature. The colder the water temperature, the more ice. But light is something that we haven't considered before. So this is both some observational data that we collected in the field, and we're also have been doing some work in raising eggs under different light conditions, and I'll show that data in a minute. So we put a light sensor out at Sand Island, which is in the Apostle Islands on Lake Superior up by Bayfield, Wisconsin, and that's that white dot off the big island to the left under the ARY of January. And we put it in the fall, and we took it out the next summer. And when we had a high ice cover in January through February, you can see there's very, very little light got to the bottom. That ice got pushed out, and that's we had a nice satellite image on the 15th of March, and light bumped right up when we lost that ice cover. So ice cover is providing darkness to those eggs, and that's fairly obvious. If we think about a potential mechanism then between ice and recruitment, we can think about how that affects larvae timing, and that's shown on the left, and that just looks at temperature. And so that's the curve is from Colby and Brook, who raised Cisco eggs to larval stage under a variety of temperatures, and this is the curve they developed from that. And the two dots are data that we collected in the field, and so those temperatures that we got in different winters. So 2014 was the polar vortex winter, the super cold winter. 2017 was a really warm winter where we had no ice, and we saw a 40-day difference in the hatch stage of cisco larvae. And on the right, it's the effect of light on yolk sac area. So on the bottom right, that circle is the yolk sac of a larvae. So immediately after they hatch in the lab, Taylor Stewart would measure yolk sac area. And these are the differences that he saw in yolk sac area under full light, partial light, and complete darkness. Complete light is not something that can happen in nature, but we wanted to see if there was, almost take a sledgehammer effect for this first experimental run. Was there an effect at all? And we did see an effect, obvious effect between full light and no light, but we also saw a significant effect between partial light, which was a typical diel cycle, and no light, which we would see when we had ice cover. What is the trend then in January ice cover? If we think about maybe January ice cover is a real factor, how has that changed over time? It's a satellite photo of this January where we had 19% ice cover on the lake. It's hard to find a clear image in January because the lake's getting cold and it's not ice covered yet, so that it's cloudy every single day. And the plot on the bottom, the yellow dots are, was there a satellite image taken? And also we could determine ice cover. And then the blue dots, which turn out to be bars because they run into each other, are days when ice cover was greater than 15%. And then the horizontal line is January 31st. And so for this, what came out in the model, you should see blue bars below this line. And they're consistently below this line up to 1998, and then they're not very consistent after that. And these are those recruitment events where the brown was the high and the pink was the medium to moderate recruitment events. And those match up fairly well, which the model then showed you before, where we had 6 of 7 came out with 15% ice cover. But we have seen, again, the big changes, we have not seen as much early ice cover after 1998. The second factor that came out in this regression tree analysis was July temperatures greater or less than 7.5 degrees. And we take this as an indication of spring warming. And 70% of the high recruitment events have a July temperature less than 7.5 degrees, and the other one fell on the other side of that line. So again, January ice cover explained 90% of the measurable to high recruitment events, and then spring warming rate explained 5 of 6 of the high events. And again, it's not crazy in terms of the biology of the fish and what we know about that and egg development. But it's a better results than we've seen so far, and again, I think we have a potential mechanism for this. If we look at the trend in July water temperature, so those are daily July temperatures on the Y year, and then that cutoff value in the horizontal line of 7.5 degrees. Again, we see pre-1998, it was right along that 7.5 degree line. After 1998, it's gone up, and then it got dropped down a little bit because of 2014 and 2015. And the black dots are that mean annual July temperature. And so what the model is saying, for there to be a measurable cisco recruitment event, you need those dots to be below that line. And again, if you think about just look at pre-1998 and post-1998. When is, this was an analysis we did, when is it decided that July will be greater or less than 7.5 degrees? And it's early, so we ran a similar regression tree model on that question, and the two primary factors that came out were January ice cover. So if you get ice early, which is also an indication of maximum ice, which is probably more what this is looking at, and also if you retain the ice later, so March ice. So if, again, there was only this one value right here that occurred to the left of this 15% max line when January ice was 15% or less, where because you want that July temperature down here. So there's only one event that occurred here. So it's pretty well set in January. And then over here in March, you see all those values are right there. So in March, if you have 68% ice cover, and again, the model spits that number out. It decides what that, it can pick any number that there's data available. So it decided on this cutoff of 68%. Again, all the values are right there. Again, those are color-coded to recruitment events, but I won't spend the time going through that now. So in summary, the overall population trend, so from our annual survey data, non-Cisco prey populations have been relatively steady over the past 20 years, or not steady, stable. And for the Cisco populations and rainbow smelt, they're much less than they were in the past. And if we compare the time period now to that earliest time period, things were similar. In an offshore, Kaiai's down. It's one of the Cisco species, so bloater's down, Cisco's down, Kaiai's down. And deepwater sculpin are stable, and Cisco lake trout have been stable. But we have seen a shift in deepwater sculpin populations moving into shallower water. The forecast, so this upper plot looks at the percent of recruitment events that have occurred in 5-year blocks. It's not good. We haven't seen a high recruitment event since that 2003 event. Even a measurable moderate event has not occurred in the last 3 years, and very few occurring again since the 2003 period. If we think that January ice cover is an important factor driving recruitment success, this has declined over the last 50 years, and that's shown here on the left. And again, with the big change occurring after 1998. If we think about the next 50 years, the forecast doesn't get any better. This just came out, and this shows for the Great Lakes, there was going to be approximately 30-year reduction in the number of days where temperature is less than 32 degrees over the next 50 years. But that said, a lot of people in this room I've heard say it only takes one event. And as Owen pointed out, recruitment and Cisco populations in general were way down in the 60s, throughout most of the 70s. In '84, we had that big event. Everything popped up and everything was great. So it just takes one event. That's the take-home message. Thank you.